engagement. Without further ado, it is my pleasure to begin my presidential address. I'm honored to have the privilege to serve as your president during this remarkable 75th anniversary year. I want to take the next 20 minutes or so to share my reflections on our past, our present, and our future. I should start with disclosures for those of you who need CME. I want to confirm that neither ChatGPT or generative AI was harmed in the preparation of this presidential address, nor did they contribute to its content. In other words, I did this the old-fashioned way. As you know, the theme of this year's meeting is One Humanity, Many Genomes. I was delighted to hear it when this was chosen, and I want to thank especially Neil Hanchard and Charles Rotimi, who were instrumental in coming up with this theme. It made me think about its many layers of meaning, and I'm sure it's done the same to you. So one humanity and or many genomes. On the literal genomic level, I don't need to tell this audience, it says that we are, of course, share much more than what differentiates us, over 99.9% of our genomes, per Sarah Tishkoff from the video. But as a medical geneticist, that small portion that distinguishes us can have real impact. For example, a single nucleotide variation can cause severe human genetic disease or give us a disease susceptibility. As a scientific community, our goal, of course, is to understand these differences also, to target its biological import and fix the medical consequences, or at the very least be informed by these differences for personal decisions. I would posit that the differences contribute to the diversity, but they are actually a strength and not a weakness at all. One might ask, how do we achieve then one humanity? I would say that it is, or will be, to appreciate our shared journeys by recognizing and learning from our history, by embracing our common present, and by dreaming together about our future. The shared journey is no different than the significant sharing of our common genomic ancestry. I would challenge all of us to carry this theme throughout the meeting and beyond, importantly, in our everyday lives. So our shared journey this year, and it has been quite a year. I started the 75th anniversary year, much like all of you, coming off the uncertainties of the first post-COVID year. For ASHG, this included regrouping from our first in-person post-COVID meeting in 2022 in Los Angeles. I am delighted to report to all of you that the Society is healthy, has bounced back, and is in great shape. This is best exemplified by your outstanding participation here for this 2023 meeting. However, there continues to be challenges to our society, to our field, and to our mission. The changing landscape in the scientific and funding community, not to mention the rest of the world, has prompted us to revisit our strategic plan, primarily to update what was already an excellent pre-COVID strategic plan from 2019. The intent was to prioritize the existing goals for the post-COVID reality. I'm pleased to report that the board has completed the work, and this will soon be released in the form of a new refreshed strategic plan. It will be an important template to guide the work of the Society on your behalf in the coming years. As many of you know, we started the year unveiling what I view as one of the most important projects of the Society. Thanks to the leadership of multiple boards and an outstanding committee that led the work, the ASHG released a report of a multi-year effort, Facing Our History, Building an Equitable Future. In 2018, the ASHG board established diversity as a top strategic priority. It charged the Society, following the heights of racial and social unrest in 2020, to conduct a review of its own history. The report and its findings were painful. The document and they document a history that must be told and taught so we can prevent its resurgence. By acknowledging our history and apologizing for wrongs, the Society seeks to form a stronger foundation for trust and inclusion in looking to the future. The board, in its immediate and future actions, strives to ensure diversity and inclusion in all of its activities and to commit to speaking out when harms are done due to misuse of human genetics. I think that the diversity of ASHG is exemplified at many levels in this meeting by the diversity of the participants, by the diversity of the science presented, by the diversity of technologies exhibited, and by the diversity of the topics discussed. It really exemplifies our strength together. In thinking about the sheer journey of our society, I thought about my own personal and professional journey in the field of genetics and genomics. As a child immigrant, product of chain migration to the US, neither of my parents were college educated. I arrived in Houston 30 years ago, this year actually, for my pediatrics and genetics training, and experienced firsthand the excitement of the epics of technology innovation that have driven discovery in our field, that have been presented every year since in this amazing meeting. This is, of course, exemplified in the transformation of sequencing technologies. As a graduate student, I cut my teeth on Sanger sequencing pieces of cloned DNA, or out of CosMed libraries, for those of you who remember what that is, and PCR fragments to identify strong effect mutations in Mendelian phenotypes. For me, that was type 2 collagen in genetic forms of dwarfism, and fibrillin and Marfan syndrome. And of course, as arrays became available, the ability to take whole genome approaches for whole genome-wide association studies to study common variants in common phenotypes. And then, of course, whole exome and genome sequencing led to the identification of strong effect alleles, finally, in common phenotypes, as well as phenotypic expansions in rare diseases. This, of course, has had an enormous impact in clinical genomics and in genomic medicine, especially in the area of diagnostics. So Sanger sequencing of single gene disorders in the late 80s and early 90s to chromosomal microarrays for copy number variation disorders, to next generation sequencing panels, exome sequencing and genome sequencing for a wide range of pathogenic human variations. And in the decades since, therapy for genetic disease in the form of viral and nucleic acid-based gene therapy has become a clinical reality, with now over 30 FDA-approved in vivo gene and ex vivo gene-modified cell therapies, primarily for genetic diseases and cancer. Not surprisingly, ASHG's top milestones parallel this personal journey. The pillars, of course, the understanding and manipulation of the structure of DNA in the human genome, from elucidating the double helix to recombinant DNA approaches, to Sanger sequencing, to identifying DNA markers, to Human Genome Sequencing Project, to the development of next generation sequencing, to gene editing, to the completion of high quality genome references. It has been an amazing series of epics of technology development. Now, applying this technology naturally followed. Understanding human variation by elucidating the number of single nucleotide variations in the genome, the discovery of haplotypes of genetic variants that could be inherited, the 1,000 Genomes Project, and the development of reference population databases. The next two pillars reflect very much the application of the first two, elucidating the genetic basis of disease and implementing that information for healthcare. They very much reflect my own scientific journey, as this was and is the space I've had the good fortune of working. Most recent, then, and next is the appreciation of what is beyond DNA with the application of technology to understand epigenetics, cataloging all the DNA elements that control gene expression and their impact on tissue-specific gene expression in general. What about the present? These epochs of technology innovation and milestones in human genetics had led us to an exciting meeting and our embrace and celebration of the present. Humans are now the best model for discovery, as human variation directly lends insight into unique structure-function correlations in proteins and pathways. They inform basic science, the hypotheses underlying the study of disease mechanisms, and drug development. An excellent example of this is the collaborative and multidisciplinary work of the NIH on Diagnosis Disease Network. The application of transformative technology to diagnostics has and continues to be the best examples of the benefits of our shared journey. This ranges from the use of whole genome sequencing for diagnosing rare disease, to cell-free DNA testing for cancer and reproductive health, to development of polygenic risk scores in common disease, to implementing RNA sequencing and metabolomics in diagnostic algorithms. The understanding of the genetic basis of human disease and the underlying pathogenic mechanisms and the diagnosis of these disorders have empowered the application of gene therapy. It's not surprising, perhaps also a missed opportunity, that the American Society for Cell and Gene Therapy was in part grown from ASHG members who focused on therapeutic development circa 25 years ago. Moreover, it is in genetic disease that we've had the many successful development of gene therapy medicines, from viral gene therapy for RPE65 retinitis pigmentosa and now spinal muscular atrophy, to cell-based gene therapy for beta thalassemia, to antisense oligonucleotide therapy for Duchenne muscular dystrophy and hereditary amyloidosis, and soon to be approved gene editing cell therapy for sickle cell anemia, with the FDA advisory meeting just having been yesterday with their recommendation to move forward. This amazing present, of course, is tinged by our challenges as a community for overcoming lack of diversity. This includes the diversity of patients in the form of health access disparity, diversity of participants, for example, in our genomic databases, and of course, diversity of our workforce, as shown so clearly by the ASHG Workforce Survey. However, we are making progress, and this is so represented by the most diverse cohort in the world today, as assembled in the All of Us research program, as well as by initiatives such as H3 Africa for building capacity for genomics and genetics in diverse communities and geographies. Our shared journey also includes emerging threats. No greater is the growing chorus of anti-science, where increasingly vocal communities and of great concern in governmental policies themselves that reject science and the scientific method as an objective method that can generate universal knowledge for the good of humanity. We must engage on this issue as citizen scientists with the highest urgencies, both as a society and together in our everyday interaction with our fellow citizens, irrespective of their personal beliefs. So what about our shared journey and dreaming about the future? What makes me most excited is, in fact, the future. There is no scientific field that moves as quickly and can change practice as quickly as human genetics and genomics. Our shared journey of the future must build on our history and present to deliver benefits of genetics and genomics to everyone, everywhere. It is to have an equitable expansion of precision medicine. This means diagnosing every genetic disease and applying targeted therapies for all diseases in all people. This also means integrating genomic information for healthcare and prevention for all. It is to increase diversity of genomics research. This means to have worldwide equitable and respectful representation in genomics. This also means to have worldwide participation in longitudinal biobanks in genomics. It is to develop new avenues for research and clinical impact. This means new approaches to treat and new approaches to test efficacy of these treatments. It is to increase awareness of genetics. This means increasing education and awareness of public health professionals and policymakers to enable informed discussions and decision-making about all aspects of society that are impacted by human genetics and genomics. So, how do we get there? Of course, we start with many genomes, And we moved to transcriptomes and epigenomes and metabolomes and proteomes and metagenomes and exposomes, secretomes, enviromomes, microbiomes, phenomes, kinomes, and many more. Ultimately, the goal is, of course, to realize the promise of one humanity. I wanted to end by personal thank yous. This is for my own personal journey that's led me here to this honor of presiding over this momentous ASHG year. I want to thank Baylor College of Medicine and the Department of Molecular Human Genetics, where I've spent my whole professional career, 25 years now since I've started my lab, especially the faculty, staff, and trainees who are my colleagues, friends, and mentors. I want to especially call out the late Ralph Feigin and Tom Caskey, who convinced a New Yorker to land in Texas. I want to thank Art Baudet, who has been my scientific mentor and chair and friend all these years, and the late David Remoyne, also, who was a professional mentor since I was a graduate student. I want to thank my own trainees and staff throughout my 25 years as an independent investigator, many of whom are here today, and I look forward to celebrating with them later in the week. And my family, who have allowed me the freedom to pursue the passion of genetics and genomics, truly unfettered. And finally, I want to thank all of you, the human genetics and genomics community, who contributed to this shared journey of ours. Thank you.